Okay, so moles and redox reactions. In the previous lesson, we discussed how to figure out the unknown oxidation states by using the set of information that could be given in the question. These were some of the rules that we revised, that group 1 will always have a positive 1 oxidation state, group 2 will always have a positive 2, and group 3 elements will always have a positive 3 oxidation state. Neutral elements will have an oxidation state of 0. Transition elements have a variable oxidation state. Oxygen has a negative 2, and hydrogen has it. Sorry. Uh, where were we? Okay. Yeah. Hydrogen always has a positive 1 oxidation state except for a hydrogen in metal hydride. A metal hydride could be any element where any compound with metal and hydrogen, for example, NaH, sodium hydride, MgH2, magnesium hydride, right? So these are all the metal hydrides. And if you see the oxygen state of hydrogen is -1 in these metal hydrides. Oxygen is always -2, but in H2O2 oxygen is -1. This is the exception. So you use these rules, the table, the information here to figure out the unknown oxidation states. We've talked about that in detail as well. And this was the assignment. We're going to move on to the application of redox reactions with moles here now. So alongside moles, you can use the redox equations to balance certain chemical equations. So the topic we're studying now is redox and balancing. So let me write down an equation here. Fe plus MnO4 negative plus hydrogen gives us Mn2 positive. So this is an equation that has compounds and ions, a mixed equation of the ions and compounds, plus H2O. So, all right, now we're going to be using the rules of redox to first of all balance the equation by looking at the loss and gain of electrons, and then we'll use the conventional balancing methods. Okay, first of all, redox. I would suggest you to first of all mark all the oxidation states. Iron, this or iron, okay, this is, let's say, given the question, iron is 2 positive. So you're first of all you're supposed to find out the unknown oxidation states. You're supposed to balance the electrons. I'm writing down these steps here. Number 1, you need to figure out the unknown oxidation states. Number 2, balance the electrons. And number 3, you're supposed to balance the equation. All right. So what you need to do here is look at the oxidation states. You were given with the oxidation state of iron, that is 2 positive. Okay. We can figure out the oxidation state of MnO4. Yeah. One of the important points to attempt this question is to know all the oxidation states. Hydrogen is positive 1. Let's just write it down. H2O2 and H2O2 oxygen is always -2. Hydrogen is positive 1. So we're only left with the oxidation states of Mn and O here. So how to figure out these oxidation states? MnO4, the whole charge is negative. All right. Let's consider, I mean, oxygen, we already know it's -2, yeah. So we can write it down here. Oxygen is -2. Now we're just left with Mn, magnesium ion. So we're going to apply those same oxidation rules. Mn is X. Oxygen is -2 times 4 because 4 is a subscript. So we're going to multiply it with the oxygen. And all of it is equal to -1 because this negative is the whole oxidation state here. So X minus 8 is equal to -1. X is equal to -1 plus 8. And X is equal to +7. So the oxidation state of Mn is +7. Are you clear with this?
Yes.
Yeah. So
We're
see the
supposed to just use like multiply. Just use the electrons. electron number.
Yeah, to figure out the unknown oxidation states.
Yes.
That's it. This is the first rule. Once you're done with that, see, you're given with all the oxidation states now. Every ion in the equation has its oxidation state given. The next step is to balance the equation according to balance the electrons. Okay, so how to balance the electrons? Let's focus on iron first of all. Okay, why are we focusing on iron? Because if you look at hydrogen, hydrogen is plus one here, hydrogen is plus one here. So we don't have to do anything. It's already balanced, right? Oxygen is negative two here. Oxygen is negative two here as well. So we don't have to do anything with the oxygen as well. So the only differences that we have are between the oxidation states of Fe2 positive, Fe3 positive, Mn positive 7, Mn positive 2. Yeah. So we need to balance these now. Both of the irons and both of the manganese ions. Okay, now look at the irons. Iron is positive one, I mean, iron is 2 positive here and iron is 3 positive here. If your oxidation state is going from plus 2 to plus 3, what does it mean? This is an increase in oxidation state, right? And oxidation is loss of electrons and increase in oxidation state, right? So can we say that this increase in oxidation state tells us that this is oxidation? There's oxidation going on here in this for the sign, yeah? So what is oxidation? Loss of electron? If the oxidation state increases by 1, so it means you're losing 1 electron. So we'll simply write iron lost 1 electron. Yeah, is this clear up till now? Are you there? समझ आ रहा है?
I'm having some internet issues. Can you repeat?
Okay. Where did you got cut off? कहाँ से बताऊँ?
Lost of 1 electron for iron.
To see how iron's oxidation state is changing from plus 2 to plus 3, right? So this is increase in oxidation state. And increase in oxidation state is oxidation. Oxidation is also loss of electrons. If the oxidation state is increasing by 1, this indicates that this iron is losing 1 electron, right?
Yes.
This wasn't a very good yes. Okay, listen to it again. Iron key oxidation state is increasing. It is plus 2 here, right? And it's plus 3 here. So increase in oxidation state is oxidation. Whenever an element oxidizes, its oxidation state increases, right? And what are the other definitions of oxidation? एक तो होगी ना increase in oxidation state. Then loss of electrons.
Loss of electrons.
Okay, so focus on this. Whenever the oxidation state increases, the electrons are lost. This is a fact. Yeah. If your oxidation state is plus 1, this indicates that you have lost 1 electron. So if the change in the oxidation state of this iron is from plus 2 to plus 3, so technically the oxidation state is increasing with 1, right? There's a plus 1 increase. This plus 1 increase tells us that you're losing 1 electron. Okay? This is why we're writing that iron lost 1 electron. When iron, it lost an electron, its oxidation state changed from plus 2 to plus 3 immediately. I hope this is now clear.
Yes.
Okay. Now look at Mn. Mn is plus 7 here and Mn is plus 2 here. So let's look at the oxidation states. Plus 7 to plus 2, the oxidation state is decreasing, right? It's going from 7 to 2, it's decreasing 5 numbers. So this tells us that Mn is gaining 5 electrons because its oxidation state is decreasing, and decrease of oxidation state is reduction. Reduction is also gain of electrons. So Mn is gaining 5 electrons. Okay. So because it gained 5 electrons, this is why the oxidation state decreased by number of 5 from 7 to 2. I'm going to just give you some basic examples there. If Na is a neutral element here, okay, And if Na loses one electron, it's going to become Na positive 1. Mg is a neutral element. If Mg loses 2 electrons, it's going to become Mg positive 2. All right. Chlorine. Chlorine is a neutral element. If chlorine gains 1 electron, it's going to become Cl negative 1. So whenever an element loses an electron, it gets a positive charge. And whenever an element gains an electron, it gets a negative charge. The fact here is that upon loss of electrons, the oxidation state increases, and upon gain of electrons, the oxidation state decreases. The iron over here, iron was losing the electrons, it lost 1 electron, so its oxidation state increased by a number of 1, from +2 to +3. Manganese over here, it gained 5 electrons, so its oxidation state increased by a number, it decreased by a number of 5, yeah? So the oxidation states work exactly the opposite of the loss and gain of electrons. I hope you're getting this. So our next step will be to balance the equations. If let's say reduction is done for this manganese ions and the number is 5, so what you're going to do is you'll multiply 5 with this 1 electron and you'll multiply 1 with the 5 electrons here. Now this means that this, because we need to balance them, we need to equate them, we need to get these values equal. Okay, so up, if this is 5 here, so we're going to multiply this 5 with both of the irons, and we're going to multiply this 1 with both of the Mns. Hua kya? Up, we have a balanced chemical equation now. The equation is balanced according to the number of electrons. Okay, once you have this equation, your next step will be to write it down here neatly. Okay, just write a neat equation again. 5Fe. You can now ignore all the charges, okay, because you're already done with this charge. I mean, you're already done dealing with all of these oxidation states. Just write these elements. MnO4 plus H is equal to Mn plus 5Fe3 positive. No, okay, we're going to ignore the oxidation state, plus H2O. So now the second equation that you have is the one that is balanced according to the electrons, right? You need to further balance it by using your own rules. You already know how to balance an equation, yeah? So if you look at, if you look at this equation here, it has 1 hydrogen and 2 hydrogens here. So an oxygen
We'll
is
be putting 2 in front of hydrogen.
yeah, but again, see, there are 4 oxygens here, and you just have 1 oxygen. So if you multiply this
2 in
entire thing,
front of H2O.
no, 4 because oxygen is
4.
1. Yeah. So this is going to become 8 because 4 2s are 8.
8.
How to? So now this equation, I think, is, yeah, this is balanced. So now this is the final equation that you have. Did you notice one thing? We didn't have to do anything with Mn and Fe because we had already balanced them according to the electrons. This is why. अगर आपके पास, अगर आप ये electrons वाली balancing ना करती ना, तो आपको आपसे balance ही नहीं होनी थी equation by using these conventional methods. All right, because this is an ionic equation. You cannot balance all of it according to just these by just following the conventional rules. Yeah, so you had to attempt this balancing through the electrons first of all, and then the conventional balancing to get a balanced chemical equation. All right, so what we do here is we look at all the oxidation states of the equation. We figure out the unknown oxidation states. We balance the equation according to the oxidation states. And then we balance the equation conventionally by the methods that we already use. And then you get a balanced chemical equation. Is this clear?
Yes.
All right. Do you want some time to note it down?
No, I already did.
All right, great. So this is how you're going to see some questions. You'll be asked to balance chemical equations according to the number of electrons, and then and by using these rules of redox equations there. Okay, we're done with moles. We can move on to the next topic. What I want you to do now is, you have the topicals with you. Try attempting a few questions. From, I mean, if you could you maybe roughly tell me how many questions there are for a particular question for a particular topic? Are those just the MCQs, or do you have theory questions as well?
No, I only have the MCQ topical.
MCQ topical, okay. And roughly how many MCQs do you have for one topic maybe?
For one top.
All right, atomic structure. This is the chapter number 2 for AS level chemistry. Uh, Atomic structure, you must have studied this topic in your O levels as well, regarding the structure of an atom, the subatomic particles, the electron shells, the nucleus, the protons, the neutrons. Yeah, you would have done everything before as well. Just letting you know that this atomic structure is pretty different to what you've studied in O levels, because we study some technicalities in depth for the structure of the atoms here. Number one, you should know that how an atom looks like. Let's say this is a hydrogen, and hydrogen has one electron and one proton. So this, let's say, is the electron on the outer shell of hydrogen. Now this electron isn't technically on that shell. It's not necessary that the electron will be at this position. Yeah, it could be anywhere. This electron could be found anywhere within this region. All right. So in an atom, you look at the probability of finding the electron in a particular region. So what you can say is, if this is an atom, okay, this is the nucleus, the positive nucleus. This entire region, the red region, is the space where you can find the electron. Getting it? So you can say that the electron can be found in this spherical region. And this spherical region is also known as the orbit. We call it the orbit of an electron. Okay, so what is an orbit, or what are atomic orbitals? It is not, an atom can have more than one orbital, more than one orbits. This is just one example here. So atomic orbitals, you should know about these orbitals. Atomic orbitals are the regions or the spaces around the nucleus of an atom that have these electrons. Okay, so definition could be that atomic orbitals are region of spaces around the nucleus of an atom where um, where the electron could be found. And there are different types of orbitals. The first type of orbital is the s orbital. The s orbital is just like the example that we just did. There's a nucleus and there's a circle, spherical orbit, and all the region around this within the sphere is it's the area where the electron could be found. All this region here. So the definition of an s orbital is the spherical region around the nucleus, the most basic example. Similarly, the second type of orbital is a p orbital. A p orbital is not a sphere. It has these two oval shaped regions around the nucleus. So imagine this is a positive nucleus, and then this positive nucleus has these two oval shaped regions on the sides where the electron could be found. So you can have electron either in the left region or in the right region. So you could say two oval shaped regions electrons can be moving in these two oval areas. Okay, you can find electron in either oval shapes there. And the third type of orbital is a d orbital. D orbital, basically the shape of d orbital is four ovals: 1, 2, 3, and 4. All of these four ovals have the probability of an electron being over there. So you can find an electron in either of these four oval shaped regions. And this d orbital is not in your syllabus, it's in the A2 syllabus. So you don't have to worry about this right now. You should just know the name. You should just know that there are a total of 3 orbitals, S, P, and D. And all of these orbitals are the regions where you can find an electron. Are you clear with this? Should we move on?
Yes.
Okay. The next thing that we study are the subshells. Subshells are basically when group of the same type of orbitals combine. For example, 3p orbitals will be known as a 1p subshell. 5d orbitals will be 1d subshell. So subshells are basically group of orbitals, group of same type of orbitals. Whenever these orbitals combine in form of a group, they make up subshells. So the first subshell is basically an S subshell. Remember that an S subshell can only have one S orbital. I mean, S subshell and S orbital is the same thing. It's again the same thing. One positive nucleus and a region around that nucleus where the electron could be found. This is an S orbital as well as an S subshell. So it's the same thing. So you can say that one S orbital makes up one S subshell. So it's basically the same thing. So now for p subshells, there has to be a total of 3 p orbitals to make up a p subshell. So remember, this is how the shape of p was, right? Two oval shaped orbitals. This is one p orbital. If you combine total of 3 p orbitals, second and third, so you're occupying the x-axis, the y-axis, and the z-axis. So these three orbitals are on all of these three axes. There is a central positive nucleus in between, and the probability of finding an electron is in all of these orbitals, the 3 orbitals and the 6 regions that we have, 6 oval-shaped regions there. So let's just color these with green. So green areas are all those where you can find an electron. Yeah. So what we can say here is that 3p orbitals make up one p subshell. And on the axis, you can call them px, py, and pz. Let's say if this is a px orbital, this is py orbital, pz orbital. All right, when px, py, pz combine, they make up one p subshell. And similarly, the last is the d subshell. Again, it is not in your syllabus, but you should just know the names of the orbitals that make up d subshells. So there are a total of 5 d orbitals that make up one d subshell. The names are dxy, dxz. You can even ignore the names. I'm just writing these here for information. You're going to study these in the year 2 syllabus. Dx square, y square, and the last one is dz square. So you should just know that a total of 5 d orbitals make up a d subshell. And there's an f subshell as well. 7 different f orbitals will make up one f subshell. We're going to just ignore that. All right. So is it clear till now, the subshells? Dua, can you hear me?
Hello.
Hello, yes, Dua, can you hear me?
Yes, I can. I just have bad internet.
Acha, is it clear to you, the subshells?
Yes, yes.
Okay. So now we need to see how many electrons can there be, right? One orbital can have a maximum of 2 electrons only. Okay. Remember, one orbital will always have 2 electrons. 2 electrons maximum in one orbital. So if there is an s orbital, it will only have 2 electrons. P orbital, because you see, again, yeah, p orbital will also have 2 electrons. One electron might be in this region here, and the second one might be in the other region. And d orbital will also have 2 electrons. Now the subshells, the electrons would multiply depending on the number of the orbitals that make up a subshell. So in a p subshell, there is only one p. Sorry, in an s subshell, there is only one s orbital. So the number of electrons in an s subshell will also be 2. But if you look at a p subshell, there are a total of 3 p orbitals, and one p orbital has 2 electrons. So how many electrons will there be in one p subshell, Dua?
6.
6 electrons, 2 for px, 2 for py, and 2 for pz. Total of 6 electrons in a p subshell. And for a d subshell, there will be 10 electrons because 2 in each. All right, 2 each, making up 10 electrons in total. So this is what you should know, that this is how the electrons are found in these subshells. Okay. Shell number and principal quantum number should know how to write these electrons, how to write a shell number. It is also known as principal quantum number. So if, let's say, the standard notation is 1s2. In 1s2, the first number, the coefficient 1, basically tells you the energy level or the shell level. S is the subshell, and 2 is the number of electrons. For example, if I write, let's say, 3p2. So in 3p2, 3 is the energy level, p is the subshell, and 2 is the number of electrons. I hope this is clear. As the shell numbers increase, the energy levels also increase. A 1s subshell will have lesser energy as compared to a 2s subshell. Okay. Okay, let's just keep it till here.
What is energy level? How will I know?
It is the level of the shell, basically. All right. Dekho, for example, if this is an element, these are the shells, right? This is level 1, this is level 2, this is level 3. So as you move across these shells towards the furthest shell, the energy level increases as the shell number increases. Yeah. Because we're going to study that in detail later on. Okay, why are these energy levels increasing? There's more, I mean, there's lesser attraction, there's more shielding. You would have done ionization energies, yeah?
Yes.
So you know the concept. So as you move across, you need more energy, yeah? Because the shielding is stronger, the attraction is weaker. So this is how the shell numbers increase and the energy levels also increase. A 4p would be at the highest energy level because 4 is the greatest number. And yeah, that's it. All right. So this is what you should know, because we will be studying about these, the filling of the subshells, these notations in detail in the coming up classes. You should know the standard notation as well, how we write these energy levels there. Any question?
No, I've studied this chapter before. It's it's a little easier. I just need to clear my concepts.
So I'm really glad it's easier for you to comprehend these topics. Just keep revising. Okay, we're gonna just so I'll try to just get done with this topic quickly. because you already know the concepts. Yeah, we'll just revise most of these in the upcoming classes. All right.